So we want to take now what we did in the last video and try to clarify the notion of dimension. You know a notion of dimension from linear algebra, the dimension of a real vector space. And there are three well-known statements that clarify this notion. Let me repeat these facts from linear algebra. The first is that if Q is smaller than n, then there is no surjective linear map from R to the Q to R to the n. Problems with my pen. There is no linear and surjective map from R to the Q to R to the n. Likewise, if Q is smaller than n, there is no linear injective map from R to the n to R to the Q. And it's a consequence, but let me state it explicitly. So if there is a linear isomorphism between R to the n and R to the Q, then the two numbers are equal. Then n equals Q. So dimension, this n, which is called a dimension, is really a well-defined notion and preserved under linear isomorphisms. That's the situation that we all know very well. And the corresponding notion in topology, where we replace linear by continuous, is more subtle, and it's also more difficult. So the topological counterpart are three statements, which I call 1 prime, 2 prime, and 3 prime. Put it a little bit above, in 3 prime, which are obtained by replacing linearity by continuity. So for the first, we just replace linear by continuous, and for the third statement, we replace linear isomorphism by homeomorphism. Yeah, and then you might ask, what is still true in this situation? If you believe in the most naive, or in the ideal world, then everything should be true somehow, because it's really hard to imagine continuous surjective maps from R1 to R2, say. It's really hard to imagine continuous injective map from R2 to R1, and same for the third proposition. But it's more subtle than that. It's more subtle than that. And it turns out that 1 prime does not hold in the topological world, but 2 prime and 3 prime are still true. And that's the theorem. And the theorem is the invariance of dimension.
Yeah, so the unprimed statements all follow from the rank nullity theorem in linear algebra. So there cannot be anything similar in topology if one of the statements is true and the other one is not.
Yeah, right. That's also a consequence of that. So invariance of dimension, to be strict here, really only refers to 3 prime. But let's collect the positive statements here. Still hold true. So R to the n being homomorphic to R to the Q implies n equals Q. But in red, 1 prime is not true. And that's subtle, right? Because in linear algebra, because of what you just said, there is no real difference between 1 and 2. So it's very easy to switch from injectivity statements to surjectivity statements in linear algebra. Somehow I find it surprising that there is a difference between 1 prime and 2 prime. So, and why is 1 prime not true in general? Because we have space filling curves. That's something we learned in the previous course. It's something that you might want to look up if you have never seen it. There are these space filling curves, so surjective continuous maps from the interval or the real line to R2. So these space filling curves are of course not very obvious, and they're usually constructed as a limit of maps from R to R2 or from the unit interval to the square. But what you can visualize are the members in this sequence of maps. And one picture is, for example, the Hilbert curve that we might check where we find a picture of the Hilbert curve or the approximation of the Hilbert curve quickly.
Yeah, drawing it would be a
no,
mess.
I'm not able to draw it, but let's search Hilbert curve.
Maybe meanwhile I can make the remark that if we can show that R to the n is only homeomorphic to R to the m if n equals m, then this also shows that dimension of manifolds must be topologically recognizable. So if you had a homeomorphism of an n-dimensional to an m-dimensional manifolds, then you can pick charts is the word in English, I think, right? Yeah, you can pick charts to see that also R to the n must be homeomorphic to R to the m. Yeah, and this is then not possible.
And you can also get a similar statement for the injectivity part for closed manifolds.
Can you zoom in there? Yeah.
In the meanwhile, there is an approximation of a space filling curve that I took from the internet. That's the approximation of the Hilbert curve. So again, space filling curves. This visualizes a map from the unit interval to the square. You get the space filling curve as a limit of such maps. It gets finer and fills more of the square more and more in each step. So 1 prime does not hold.
But can you zoom in there? Maybe I don't know if it's going to be visible.
It's resolution dependent, so it's not really a PDF.
Ah, there we go.
But maybe it's better. Yeah.
I mean, it's actually good to see that if you zoom out, then it's just some gray thing, just some gray solid thing, because this is exactly the idea. Yeah.
Okay, I want to prove 2 prime and 3 prime. 2 prime is a bit more involved and it uses what we did in the previous lecture. 3 prime we could also conclude from what we did, but 3 prime is actually extremely easy with all we have now at our disposal, meaning homology theory. So let's start with a proof of 3 prime. Which is the statement again that if you have a homeomorphism between R to the Q and R to the N, then N equals Q. Okay. So that's the statement I want to prove. And the easy proof, easy if you have homology theory, goes like that. Pick a homomorphism. Pick a point. Let's call it x0 in R to the Q. Then the restriction from R to the Q minus that point x0 to R to the N minus the image point is still a homomorphism. But this is, and we've seen this now many times, just homotopy equivalent to SQ minus 1 and here SN minus 1. It's actually the SQ minus 1 is sitting inside this Q plane and there is a deformation retract from that space to that space. And therefore, in homology, or let's say reduced homology, why not, we get an isomorphism in all degrees. Which is good because the dimension can be read off from the homology. It is the unique degree, or q minus 1 is the unique degree where this homology does not vanish, and therefore q has to be. So, by the computation of homology, or homologies of the spheres, we obtain q is equal to n. So that's...
And one also nicely sees that this also works in the manifold version. If there was a q manifold and an n manifold replacing r to the q and r to the n, then you could take out a point and then excise the complement of a ball.
Right.
And then you get exactly the same contradiction.
Right. If you excise a point in the manifold, then you're, yeah, as you said, I'm just repeating. Yeah. Mm-hmm. It's still a good exercise to write down this little argument. Now, what about the more involved statement 2 prime? Is it 2 prime? Yeah, it's 2 prime. So the statement is there is no continuous injective map from r to the n to r to the q if q is smaller than n. Let's prove that by contradiction. So proof of 2 prime . So suppose there is, so q is smaller than n here, suppose there is such a map, let's call it also f, from r to the n to r to the q, injective, indicated by this hook, and continuous. All right. What I then do is I look at the composition of this map, and then I view r to the q in a canonical way as a subspace of r to the n. So that I get a self-map from r to the n to r to the n, which is still injective, and continuous, of course. What can we say about this map? We can now use a theorem we proved in the last lecture, the invariance of domain. And this invariance of domain in that situation just says that the image of this composition is open in r to the n. So let's so consider this map. Its image is open in r to the n by the invariance of domain. But at the same time, its image lies in this hyperplane, in this q-dimensional hyperplane of r to the n. But such a hyperplane, or a subset of it can never be open in r to the n. So this is a contradiction, and we've shown it's not possible that you have such an injective continuous map.